Hi, I'm Randall Heyman, a university mathematics academic. Many students have had their learning impacted by the coronavirus, or they're likely to. So I'm making these YouTube channels to help. So if you're a lecturer, tutor, high school or primary school teacher, parent, grandparent or student, and you'd like me to make a video about a mathematical problem or concept, or anything mathematical, let me know in the comment section below the video. A lot of these have been pretty serious university level videos, but I'm happy to do secondary school. And as I said in one of the early videos, I think I can remember most of the primary stuff as well. Okay, so this is now the third item that I was asked to talk about by a class in California. We've done zero divisors, done polynomial rings, and now we're talking about quotient fields. Now, I'm not sure if this will be part one of two parts or maybe just the only part, I'm not sure. So we'll worry about that later. Okay, so the first thing I want to make, the first point I want to make here is that there's a lot of terms here that mean the same thing. So quotient field is what we're talking about, but you'll also sometimes hear it talked about as being the field of fractions, which in some ways is a better name, as you'll see. Also, fraction field, or sometimes even see field of quotients. So just be aware of that. Now, the next thing to do is realize that whilst we talk about quotient fields, and we've spoken about rings and groups, and there's this continuum of groups, then rings and fields, I don't want you to think that we can use what we're talking about today to apply in the same way to groups and rings. So not the same idea as quotient groups, nor quotient rings. They're quite a different beast, so don't get confused there. Now, the third thing is that to explain quotient fields, it's not terribly difficult once we just get the concept of the integral domain, which we talked about before in one of the previous videos. I mentioned it, so we'll just explore that in this video, and then the quotient fields will flow very naturally from that. So remember, integral domain, we're thinking the integers. The integers are the sort of the classic example of an integral domain. Now, I can actually, as it turned out, I can actually go back to what I did in one of the previous videos, because this will enable us to talk about integral domains quite easily. This is the setup I had to explain fields. We've got addition, multiplication. Down here, we've got the different rules, closure, commutativity, etc. And across here, I've ticked. For fields, we have to have, for example, this one here, associativity. Let's just go red here. So if we go here, associativity for addition, well, we have to have that there. We can see it for a field has to have that property. And likewise, it has to have this one here, commutativity of multiplication. Now, for the integral domain, essentially, we don't have this very important one, which is the inverse. I think I've mentioned that before, that if you look at what's the inverse of 2 in the integers, the inverse is a half, but a half is not an integer. So that's just reflecting that point. So this, what I've got here, is very close now to what is an integral domain. We just need to add one more tick, which is sort of a separate thing, which is that it has no zero divisors, which we discussed before as well. So there's videos on all of these terms if you're not sure. So now let's go back to here, and put this up here. So let me just talk about what is an integral domain. An integral domain is a commutative ring So I'll talk about this as I put it out here. So we start with a ring. Now remember, a ring has to be a group. We started with a group to get the ring. The group is commutative for addition, or as an abelian group we called it. So the commutativity of addition is catered for in just designing any ring. It's already there. But we didn't have commutativity for multiplication. So what we're saying here is if you want an integral domain, you take a ring, but you make sure that it's a commutative ring. The next thing is, we said that some rings don't have a unit of multiplication. In fact, the definition of a ring that we used does not include a requirement there's a unit of multiplication. So in the integers, there's this special number 1, which has the property that if we multiply by 1, it doesn't change the number. So we have to have a unit of multiplication, and so it's a commutative ring and no zero divisors. So it's important that there's no zero divisors, and that is an integral domain. So I think that's all I want to talk about in this video, but I'll record the next video very soon, and we'll work out exactly what a quotient field is once we've now understood what an integral domain is. Any questions on anything I've been talking about or any aspect of mathematics, please leave a comment in the video section below and I'll be happy to try and help you out.